So in this video, we're going to look at Jacobians and calculating a change of variables for a two-dimensional example. Now, there is a fairly long process that is involved depending on how the problem is presented to you. So we're going to look at sort of the worst case scenario where they just give you sort of a region and the shape of the region, and they don't give you any of the boundary equations to start with. And so we're going to go through an example where you have to generate those equations yourself. Now, in some cases, they're going to give you the change of variable. They're going to give you the boundary equations in a more compact way. And so some of these initial steps will not be necessary because that information is already available. But let's look at our example. So we want to find the volume of the region lying below this particular function over the region bounded by the parallelogram given by these vertices. So what we want to do first is we want to look at our points, and we want to calculate the slope of the lines that connect these graphs. Now, the slope here is going to be the same as the slope here because they told us it's a parallelogram. And then the slope here and the slope here are also going to be the same. So it helps to visualize it because that way you know which two sets of slopes are going to be the same and not calculate, like, for instance, across the diagonal, because that's not one of the boundary conditions. So here we're going to calculate between 2, 2 and 4, 4, which will be the same as between 4, 0 and 6, 2. And then we're also going to calculate between 4, 0 and 2, 2, and then also between 6, 2 and 4, 4. Again, not across the diagonal, on the boundaries. So we calculate our first set of slopes here. We get 1 for both this set and this set. And for the second two sets, we get -1 and -1 in this case. And then we need to calculate the equations of the lines that go through these points with these slopes. So again, for each of the slopes, we need 1 point that we use to generate the slope. So for line 1, when we plug that in with our 0.22, we end up with x minus y equals 0. If we do line 2 with our slope of 1, between the point 4, 0, we end up with x minus y equals 4. If we do the same calculation here with line 3, y minus 0 and 4, 0, that's this line right here, that's the -1 slope, we get x plus y equals 4. And the same thing for this one, line 4, plugging in the 6, 2, we end up with x plus y equals 8. Now, what's important for a problem like this, and what will often happen, is you will get these expressions, and now notice I haven't solved them for y. I've left the x and the y on the same side of the equation because if you look back at our function, there is already an expression with x plus y and x minus y in our function. So this function and this region go together. And so that can give us information about how we want to do our substitutions. So once we have determined that we have two equations that are the same in x and y but differ by a constant, we're going to be able to make our substitutions. So x minus y is going to be u, and then x plus y is going to be v. Now, when we rewrite these, we're going to end up with a rectangular region in the UV plane. And that's what we want, because working with a parallelogram like this, if we were to try to integrate this function as it was, not only would it be messy because it's essentially a product rule we would need integration by parts in both x and y. We would also have to split the integral up into two regions with these crazy boundaries on either side. And who knows what that would do when we integrated the first term, whether we would even get something we could use or would make it worse in the second integration. But when we change this, when we do this transformation, we get a rectangle, which means our limits are constants. Our limits in U will be between 0 and 4 because that's what the boundaries in our two x minus y terms was. And in the second direction, they'll be between 4 and 8 because that's what the bounds on the x plus y were in these two functions. All right, so now that we have our transformations, we can replace our u and our v in our equation. X plus y gets replaced with v, and x minus y gets replaced with u. And so our integral is now this. But we have one more step to do before we can actually integrate, and that is figuring out what dA is. And to calculate dA in terms of du and dv, we're going to need to calculate the Jacobian. Now, the Jacobian is essentially a matrix of partial derivatives, and we're going to have to solve our u and our v equations for x and y in order to do this. So that's our next algebra step. We're going to treat this like a system of equations. So u is equal to x minus y and v is x plus y. So if we add them together, we're going to cancel the y's. So u plus v is 2x. Therefore, x is 1/2 u plus v. And then if we put a minus sign in front of the v and we do the same thing, we can cancel the x's. U minus v is equal to negative 2y, which means that y is equal to 1/2, and I distributed the minus sign v minus u. Now I can take these partial derivatives that I need for my matrix, take the derivative for x in terms of u, take the derivative for x in terms of v, derivative for y in terms of u, derivative for y in terms of v. So the derivative for x in terms of u is going to be 1/2. The derivative of x in terms of v is also 1/2. The derivative for u in terms of the derivative for y in terms of u is negative 1/2 because of this negative sign here, but the derivative for y in terms of v is only 1/2 again. And so our determinant of this matrix, if we plug in our 1/2 and our negative 1/2, we get 1/2 times 1/2 AD minus negative 1/2 times 1/2. So negative negative becomes a positive. So 1/4 plus 1/4 is 1/2. And that means our dA is 1/2 times du dv. So by doing this transformation, we've actually rescaled the region also. And so by multiplying by the result of our integration by that extra 1/2, we will scale it back to the value that it would have been in terms of x and y. And finally, we can integrate, we can pull the 1/2 out, and this doesn't require any integration by parts because there's only v and u separately. And so when you actually do this integration, you end up with this. Now, I do want to remind everyone, though, as we do this, watch the order that you're doing your integrations in. 8 and 4 was in terms of v, so you have to do dv first, and then 0, 4 is in terms of u, so that is done last. And so that's how we get this expression. And as I mentioned, in a lot of examples, they won't go back to like just the points on the plane where you have to come up with the equations yourself. In many problems, they will give you the function, and sometimes they will tell you what the x and y substitutions should be, or they'll at least give you the boundary functions. So they'll tell you it's bounded by this equation, like 1/2 x equals y or something like that. And so they'll already give you those boundaries. And so some of these problems are not quite as long as this, but the steps should still be carried out in more or less the same order.